Okay, great. Hi everyone. My name is Cody Rue. This is the Church of Logic, and today I'm very happy to be with Andrej Bauer, who's a professor at the Faculty of Mathematics and Physics at Ljubljana. Am I pronouncing that right? In
Right.
Slovenia.
Yep.
And Andrej works on a variety of really cool things, which I feel are at the intersection of logic, mathematics, and computer science. And so hopefully today we'll be able to talk about all those things and how they interact. And basically the theme is synthetic mathematics.
Hi.
All right.
Yeah. Hello, everyone. It's great to be here.
It's really great to have you. Let's jump right into it. I've talked already. I've made many episodes where I don't go into as much detail as I'd like, but basically I've already talked about intuitionistic logic, but for only a few minutes. So can we like sort of try and get the gist of intuitionistic logic and why that may be a cool thing kind of on its own?
Yeah, so there are several ways that you can approach intuitionistic logic, I suppose. And the traditional one that people see, like the historic one, was, I think, fairly philosophical. But I think in the sort of the new generation doing intuitionistic math just sees intrinsic value in doing it essentially because it's more general than classical math. I think that is like, if I had to give one short reason, I would say that's because it's a generalization of of the mathematics, so I think many mathematicians could just relate to the fact that if you study something that's more general, then perhaps it's more interesting, although you have to have some additional motivation, and we can probably
Right,
talk
right.
about it.
Let's talk about it. So
Yeah.
so the way I motivated intuitionistic mathematics is I think the possibly the historical one, which is that it has some extra nice properties of classical mathematics. So in some ways, I don't always do things in complete generality. So I basically defined intuitionistic mathematics as mathematics without the excluded middle. That's kind of an oversimplification. Um, but removing that axiom, which is kind of going in the opposite direction of what you suggested, removal rather than an addition.
No,
Um,
wait. Let me stop you there. If you remove an axiom, then you get something more general,
that is true. Yes, that is true.
right? You take commutative groups, you take out the commutativity
Right.
axiom, you are
Great.
more general. Yeah.
Perfect example. So yeah, so you remove something, you get something more general. But the beauty of this is at first sight that the existence property, right? If you prove an existence in intuitionistic logic without this axiom, you get a more powerful result, which is to say you can actually sort of point to the object in some sense. You can actually, hold it in your hand, which you can't do if you have the excluded middle. Um, I'm often interested in the historic, aspects of things. I think historically, intuitionistic logic was exciting, but still somewhat to the side of what the mainstream of mathematics, regularly considered or considered in its most mainstream form. Um, but okay, but let's okay, so we've noted that removing that axiom makes things more general. Um, let's see, how do we go from here? In the case of groups, in the example of groups you gave, right? We have commutative groups, we have plenty of them. You remove that axiom, now you have non-commutative groups. Now you want to know, hey, are there non-commutative groups out there? So what's the analogy here with intuitionistic logic?
Right. I mean, it's a good question, right? Because you say, okay, I mean, I removed the excluded middle. Now I do some weird math. How do I know it makes sense? But can I just back up just a little bit?
Yeah, of course.
Give sort of this to compare what you said about existence with maybe a simpler situation that is better known. Okay.
Yeah.
So the idea is, essentially the idea that you're explaining is this: let's avoid using a certain thing. In this case, for you, it was excluded middle, because if we do, then something nice will happen, such as whenever we prove that something exists, it'll actually have an algorithm or an explicit construction for it, right? So do we know other examples like that in math? And the answer is yes, all over the place. So let me just give you a very simple one.
I'd love that.
Right? So by restricting yourself to a certain setup, it's going to be more difficult to do things because you are restricted, but there will be payoffs, okay? So for instance, if you write down an expression that signifies a function, okay? And this expression only uses plus, times, minus, sine, cosine, and the exponential function, right?
Yeah.
Will it be differentiable?
Yes, I see. Yeah, I see where you're getting at, and also, yes, it will.
So it will be, right? Because of the form of your argument. The form of the construction guarantees it will be differentiable. So it's exactly the same with intuitionistic logic. The form of your logic, the form of your mathematics will guarantee that certain nice things happen. And the one you alluded to is that things will be very explicit, or that they will be computable, or that they will be continuous. That's another one, right? So what the beauty of this is that it's not going to be one single benefit. It's going to hit, it's actually like a spectrum of things.
Yeah.
Right? You reap different benefits by going to different kinds of models of intuitionistic mathematics. And you ask, how do you know it makes sense? Well, it makes sense because you build models. Not only do you build models, these models arise in nature, so to speak, right? They existed before people figured out that they were relevant, right?
Well, yeah, that is definitely a different.
Some of them, not all of them, but definitely Grothendieck toposes, for instance.
Great, yeah.
Were not created with a view towards modeling intuitionistic math.
Yes. All right. So we're basically already arriving at the punchline of what I wanted to talk about, which is, hey, we look at logic, we remove, we change it in some way, we make it slightly more general, and hey, guess what? That more general setting has tons of models which weren't in the original setting. I think there's a subtle point here which is almost invisible to logicians because they're bathed in this since children, which might be visible to mathematicians. And I definitely know students struggle with this, which is basically when you think about classical mathematics, and in particular set theory, which tends to be kind of what as baby mathematician, people told me, okay, well, set theory is the basis of everything, and everything you do is all the time, underneath there's set theory everywhere. And so in some sense, you have two logics, right? You have the logics that you study like groups, there's a bunch of axioms and there are a bunch of models. And then there's the underlying substrate in which you're doing all of your mathematics, which logicians would tend to talk about as your meta theory. And you think of that thing as being kind of unique. It's this unique thing with a unique model. Now, of course, that can't be, mathematically quite the case for various reasons. But it's worth noting at this point, and maybe you have a better way to explain it, that this classical substrate of set theory that you work in, you can choose either to work in it from the inside or to look at it from the outside as just a set of axioms.
Well, yes. Okay, so I think what you're alluding to is the sort of moves that logicians perform, right? Where you are looking at the meta theory versus the object theory. Is that what you're talking about?
That is what I'm talking about. I think the point.
Yeah, that's a very unusual move for like what I would call an ordinary mathematician, right?
Yes.
But I think that's not actually. I wouldn't say that's in any sense the essence of intuitionistic mathematics at all.
I see. I personally, I'm very fond of that move, and I also feel like this synthetic mathematics idea feels tied to this move, where you say, hey, there's intuitionistic mathematics that you can work as using your foundation, and then there's models of this mathematics which happen to appear everywhere in as things you define in classical mathematics. And I feel like this move from the inside to the outside is what's appealing to me, at least. And it's appealing for philosophical reasons, but also for pragmatic reasons, which is I know how to do proofs in intuitionistic logic. I know how to pretend those things are all the things. And then I can use that intuition to reason inside these objects that I'm much less familiar with. But it sounds like that's not really how you conceptualize things. So I'd be interested to
No, I don't think so. I mean, I think I wrote somewhere that that's the bargaining phase.
that's the bargaining phase.
Yes. So
sorry. So let's see.
yeah.
For
So let's see.
listeners,
Let me okay. So um, of course, what you're describing is very useful and is what people do because it's what connects the different worlds is that you view them as models and then you can relate them and so on. First of all, why is this stuff not tied to intuitionistic logic? Because you can do precisely the exact same thing with classical logic. You take classical set theory and you start building models, and you have a model in which every set is measurable, and you have another model where something weird happens with the Cantor's hypothesis, and in fact this is a well-studied area, and so you see that you can just do the same thing there. Okay, right. So what I'm more interested in is what is the intrinsic mathematical value of doing all these things. Like what does a mathematician benefit from, say, working in a world where everything is measurable? Is this right? What kind of mathematics arises? That's what motivates me. And if that's what motivates you, I think then you don't necessarily need to know so much about the meta level logical stuff, although it is still very important that you're informed about it, because it's what helps you. It's to me it's going to help me create one of these worlds if I'm after creating a world, right?
Yeah.
So you want to say, I want to have synthetic topology, whatever that might be, and then you're going to very quickly start thinking about, well, okay, but what would be some good axioms? And well, good axioms will be suggested by good models, right? So I'm not downplaying the importance of models. Sure. I'm just saying I think I have a slightly different point of view there of what they're about.
Okay, so this is a part I'm excited about. Let's talk about some models of intuitionistic logic. We haven't really drilled down about what axioms we're thinking about specifically, but I don't think we should necessarily. What's like the first kind of reasonable model of intuitionistic logic you'd want to explain to somebody to like exemplify this point of view of like, hey, intuitionistic logic can help you think about ordinary or classical rather constructions in math.
Right. So somebody who's not familiar with intuitionistic math, probably the best way to go about it is to explain what a model looks like. I think definitely. I don't know, like that seems a reasonable approach. And I would say that there are two possible paths, and it really depends on who you're talking to. If you're talking to somebody who's familiar with computer science and in particular computability theory and things like Turing machines, that's going to be one class of models, namely realizability models. And if you're talking to somebody who is very strong at geometry and topology, then I would probably go the way of sheaves and explain sheaf theoretic models. And each is going to bring in a different kind of feeling for what intuitionistic math is about, right? Because it's like spherical and hyperbolic geometries. They will both be good examples of non-Euclidean geometries, but they will look different, right? But they will both, right? So I don't know.
We're not explaining an analogy with an even harder analogy, but that's depending on the viewers, of course.
Yeah.
So I think we can do both. I feel like what I talked about in past episodes touched roughly on this kind of this computability world. again, I'm using this world terminology, but if I talked about models of intuitionistic logic at all, it would have been a realizability model.
Yeah.
So what? Yeah, what does such a model look like roughly? And maybe we don't need to go into too much detail here.
Okay, so I would say, the first thing to understand is that it's going to be a lot like sets with some additional structure, and that is not at all unusual in mathematics, because after all, a group is a set with an additional structure. Yeah. A topological space is a set with additional structure. So this is a very common thing. What is this additional structure? Well, it's going to be an additional structure that brings in computation in some way. So the way you do it is that you pick, let's just be quite informal, okay? So you pick your favorite programming language, okay? It has to be a reasonable one, like maybe lambda calculus, Turing machines.
Sure.
But pick some programming language, and then whenever you have a set, you never just have a set, you always have a set with an additional structure which explains how the elements of your set are implemented in your programming language. So, for instance, you would never have just a graph, right? Like points and vertices. You would actually have, you would say, okay, it's a graph, but it needs to be represented by a list of adjacent edges or whatnot, something.
Right.
You would,
yeah.
Right? Okay, so then you say, okay, so my sets carry this extra information on how the elements of the set are implemented in my programming language. What's the data type? What is the specifics of encoding things? And once you have that, you can now start talking about what it means to implement a function, because a function from one of these enriched sets to another one is just going to be, well, it's a function, but there needs to be a program which operates on the programming side of things, right? That's the basic idea. First of all, I think this is completely naturally, implicitly done by programmers all over the world all the time, right? It's totally natural.
Yeah, so programmers, mathematicians forget the program part, and programmers forget the set part, right? They only have the encoding.
But you really should be thinking of both of them together, right?
Right. There's the meaning and the...
So you do, and then this gives you a category. And then this category is not yet good enough. It doesn't have enough structure, but then you churn your mathematical technology, you generalize this so that, so in particular, the thing that you're going to notice at some point is that there's something weird going on with equality, and that you need a better notion of equality, so that you actually don't explain so much about how elements are represented in your programming language, but how equality is represented in your programming language, the quality of elements. This is maybe a technical matter, but I'm just saying there's going to be some moves, and you'll arrive at a category that is good enough. So what does that mean? It's a topos, right?
Sure.
Topos,
I say sure. Yes,
yeah.
It has a structure of the thing that is called a topos.
And why is that important? That's important because once you know that it has that kind of structure, that means you can interpret higher order intuitionistic logic in it with natural numbers. And now if you have natural numbers and higher order intuitionistic logic, you have things like natural numbers, the power sets of natural numbers, products, quotients. So you can make integers, you can make rationals, you can make reals, you can do a lot of math this way. And so you essentially know that your category is this mini world of mathematics, which is somehow going to be slightly different from what we're used to. In this case, everything is going to have this built-in computability all over the place, right?
Yes, by design, but also
by design.
Luckily, that stays even after you put in, the magic powder of making this into a category.
Right. So it's still going to be there, right, by design. So you now have a model where, so to speak, computability is built in at the very low level. It's like, it's omnipresent, right? And here is an interesting thing. Because it's omnipresent, it becomes a little bit invisible. So this is a strange thing to say, but it's like You know,
It's like the fish that doesn't know about water.
yeah. It's a bit like that, or you know, I don't know, people in Japan noticing that everybody has black hair, right?
Right, right.
They first have to see a weird European.
Yeah.
So it's a bit like that, right? It's something that is everywhere. So because it's the background.
Yeah, you don't
more
keep
difficult.
it in your at the forefront of your mind.
So one of the interesting things is, how do we speak about this omnipresent way in a useful way, right? Once you're inside the topos, which means once you speak the internal language of the topos, that is to say, you speak you say, I'm now going to use only the intuitionistic higher order logic.
Sure.
And try to say things about my world this way. This is your first step to synthetic mathematics.
Yeah, I guess I don't want to overextend the analogy, but in groups, right, you could define a specific group, like the symmetric group of permutations. And
Yes.
you could talk about permutations as permutations, functions that shuffle, or you could just say, I just want to say the things that group theory allows me to say, like equality.
But by group theory, do you mean the theory of a group?
Yes, I mean,
okay,
yes,
so yes, that's going to be
theory of groups.
Yes.
And there you could say, hey, what can I say just using, what groups give me, which are products and,
unit products and inverses, right?
Right. Yeah, that is very poor. Maybe you want to sprinkle in some constants and stuff like that.
Well, but you will be able to say things like, suppose you're in some particular symmetric group, you can say lots of things. You can say like, oh, there's an element of order 4.
Right.
Or you could say, you can say, oh, there are 2 elements of order 4, and if I multiply them this way, then this thing happens, right?
Yeah.
But there will be also things that you cannot necessarily say in this very impoverished language, right? So it will be difficult to say that there are 3 elements. It might be difficult to say, depending on what the group is, it might be difficult to say that it's finitely generated, for instance.
Yeah. Great. Perfect.
Right.
You've managed to take the rough analogy and make it relatively precise. So now we're in a world where we can use the tools of this language, which is intuitionistic higher order logic, and we can say a bunch of things. And great. And now we can do all our usual constructions, but magically, but some things will be true about the world you now live in, this world of computable sets that can be expressed in this language. Can you give like cool examples?
I can give you a cool example, because it's my favorite axiom of synthetic computability. It's first of all, the topos we're discussing is called the effective topos, just if anybody wants to be precise here. Consider the following statement: there are countably many countable subsets of the natural numbers.
Countably many countable subsets of the natural numbers.
Okay, so let's first take a classical view of this. Okay, the classical view of this is complete nonsense, because obviously every subset of the natural numbers is countable. So all I said was that the power set of the natural numbers is countable, which is false.
Yeah,
so this is a blatantly false statement. Yes. However, in the effective topos, this is a true statement. Right?
So you look at all the subsets of the natural number, you cut out the ones which happen to be countable, which classically would be every subset.
Yes.
But here, being countable is a little bit more subtle.
It's something, clearly it has to be something different, right? And then what happens is you get countably many.
Great. Okay. This is a surprising axiom.
It's a surprising. This is a nice axiom to have, because it has lots of nice consequences, as it turns out. But first of all, it's a statement that is valid in the effective topos, and you can ask why. Why? Well, it's because that underlying computability structure is doing something for us. And when you ask what is it doing, well, when you say a countable subset of n, that will actually mean that this subset is equipped with an additional computability structure, which in this case will mean there's a Turing machine or there is a program that enumerates its elements. So to say countable inside the effective topos is to say computably enumerable outside the effective topos. And now if you know a little bit of computability theory, you will say, aha, but the countably enumerable sets have a numbering. They can be nicely enumerated themselves.
Yeah, not only are they countable, but they are actually enumerable. Like
they are countably many. First of all, they are countably many, countably enumerable sets, and moreover, this itself is computable.
Right. And this
so
is
that's
kind of
what validates it.
The miracle, in some sense, the miracle of computability, right? Is that you can enumerate all the enumerators.
Yeah.
Right.
Can you press pause? Somebody's knocking.
Oh yeah, of course.
Sorry.
Yeah,
okay.
No worries.
Where were we?
So we were saying, okay, miracle of computability, innumerable, computably enumerable sets are computably enumerable. This means that the axiom that there are only a countable number of countable subsets of n is true in this effective topos world of mathematics. And I was going to add, perhaps, that you're a little bit on a knife's edge here, right? Because it is true that in any, in intuitionistic mathematics, so any model of mathematics that satisfies, intuitionistic logic, all countable subsets of the natural numbers, that cannot be countable, right? The Cantor theorem still holds.
Yeah, the Cantor's theorem that says, so Cantor's theorem states that the power set of, Cantor's theorem will imply that the power set of natural numbers is always uncountable. So if you take all subsets, that's always uncountable. Right. By the way, also if you take the decidable ones, it's always uncountable. So the countable sets, of which there are countably many, is sandwiched between decidable and general, both of which are uncountable.
Right.
It shows you that intuitionistically countability does not measure size at all.
Well,
measuring something
at least not in our naive intuition.
Yeah, I don't think of it as measuring size. It's not really. In fact, or maybe you can say it's measuring size, but with the proviso that size is not linearly ordered intuitionistically.
Right. Yeah. Okay. Great. Okay. So cool. So now we have something where, hey, we can apply our intuitionistic intuition, which might be different from our classical intuition, but still, it exists. And also, it has this power of our ability to write down axioms and play the symbol pushing game if we like to, right? Which I personally do, right? That's kind of cool. And you mentioned this axiom has cool consequences, so maybe you want to mention some of those consequences.
Right. So on itself, it has consequences which are more or less basic results in computability theory. You really want a couple of other axioms in addition to this one so that things start to work nicely. So you want Markov's principle, and you want so that one is quite helpful. And then you want countable choice also, which happens to be.
Let's say we have those. Let's
say we have those.
Then
you can start proving things, which once you translate them, you unravel what they mean in the model. You discover that they're related to classical theorems in computability theory.
Right.
Okay. So what do I want? Okay, so one of them is that all functions are continuous. That's known in computability theory as the KLST theorem. Another one,
That K
Weisler
surely is
Combe
Kolmogorov.
Schoenfeld Satan. Yeah, yeah. The
So
beauty of
okay, so let's just clarify here. I think I know the answer, but here by continuous, you really mean functions that take in reals and return reals are continuous.
Yep. Yes.
And
All of them, right?
Yeah, all functions from reals to reals are continuous, which of
Right.
course is very false in classical mathematics.
Right.
And it's so false to the extent that makes this seem impossible, right? It's like a first listener who's a classical mathematician can say, what the heck? You know,
Well,
we're
yeah,
in a
because you
logic.
say, how about let's take an example, right? The sine function, which is -1 on the negative reals and 0 on 0, and then it needs to be 1 at the positive reals. And you say, how is that not a function?
Yeah.
Well, the question, do not forget, in this topos, every function must be equipped with an algorithm computing it. So if you think that you can compute this function, you should produce an algorithm. But then if you look at the details, you will see, aha, I'm supposed to calculate the sine, and the real is presented to me by a series of ever better approximations.
Yeah.
So essentially, I can look at these approximations. Okay, if one of them becomes good enough so that I can guarantee that the number is negative, then I output -1. Symmetrically, for if it becomes good enough so that I can guarantee it's positive, I output 1. But in the unlucky case that as I'm looking at these approximations, I can't quite, they hover around 0. You can't actually tell which way they're going to go. Then I don't know. I will never know an answer. So there's no algorithm, right?
Right.
And the formal proof that there is no algorithm is if you had such an algorithm, you could implement the halting oracle. That's like an exercise for your computability class. So right. So this thing is not going to be a function in this topos.
Great. Yeah. I don't know if this is a very good way to think about it, but I feel like in some sense, right, equality is a little bit fuzzy over the reals when you're talking about constructive mathematics or intuitionistic.
Yeah, you have to be careful about it because it's not decidable.
Right. And so defining things by cases, which mathematicians do all the time, is now restricted. Perhaps not completely prescribed, but very restricted.
Yes.
Great.
Okay, so another theorem is going to be a recursion theorem from computability theory, takes a synthetic form. And the synthetic form says, so it's going to be a little bit difficult to explain this only in words, but it says the following. Suppose you have some set or object. You have an object S.
Mm-hmm. And
then you look at all the object of all sequences in S. So that would be S to the power of natural numbers. Okay?
Okay.
I suppose that turns out to be countable. Okay?
Okay.
Then every multivalued function on S has a fixed point.
This
turns out to be very powerful. Yeah.
Sorry, remind me what a multivalued function is.
So every multivalued function from S to S is a function which takes an element of S and gives you some inhabited set of results.
Okay. So
it can give you many results.
Yeah. It's like a non-deterministic function.
Yeah, it can be non-deterministic. And it's going to have a fixed point.
Great. And so a fixed point, remind me what that is in this.
So there will be an X. So you will have your function F, which takes will take some, the fixed point of F will be some X in S such that F of X contains X.
Right. Okay.
So because F of X is a set of possible results and X will be one of them.
Great.
Okay.
Yeah. Okay. So if you think of that function as a non-deterministic function, it is a fixed point of X would be it takes an input and returns possibly that same input.
Right. It may, but some other non-deterministic results might be possible, but one of them will be the thing you started with.
Fantastic.
Okay. Every function on S will have that property.
Great. And this, of course, is not true.
So let's put on our classical hats and think about what I just said. Okay. So I said, suppose you have a set S such that if you look at S to the power of natural numbers, you get something countable.
Oh yeah, okay, that's already weird, right? That's already hard to
Yes.
find.
Well, that just says S has one element.
Okay, yeah. Then
Okay.
you're like, oh, well, okay, that's already true, but
Yeah.
it's true for the worst of reasons, which is it
Yeah.
never
So
happens.
right.
Almost.
So actually, I misspoke a little bit. The theorem I presented, namely that if S to the power of n is countable, then every multi-valued function on S has a fixed point. That theorem is just true intuitionistically, therefore also classically.
Right, okay.
What the effective topos gives you is lots of interesting non-trivial S's.
Yes. Yes.
That's the point.
Right.
Okay.
So
So in fact, this,
classically, you're like, okay,
yeah,
this is a
yeah,
theorem. You can prove it intuitionistically
yeah,
using something somewhat complicated because classically this just only happens for the one element set, which of course, sure, every multi-valued function that returns, a singleton, yeah,
yeah,
it has a fixed point.
yeah,
But here you're saying, hey, no, countability is more subtle. You can have countable sets which are definitely, which sequences of, the set of all sequences can be countable for subtle reasons. But hey, this theorem still holds, and
right.
you can use it all over the place.
And then you get interesting examples. And in fact, this is a little bit of a general approach that you can take there. Is you find a theorem which is just holds intuitionistically, therefore also classically. But this theorem is totally trivial classically. You have to go into a strange world of intuitionistic mathematics to find a model where this theorem actually has some power and it gives you interesting examples. So yeah.
Great. So this is like you're saying this is a good strategy to produce interesting
Yeah, it's
papers.
not such an unusual strategy. For instance, there will be theorems in algebra about rings, which are totally trivial if you try to apply them to commutative rings, right? But there are deep theorems about general rings. So it's a little, to me, it's a little bit like that, right? By allowing yourself to think more generally, that is to say, think about possible worlds, admit that there are other worlds of mathematics, and start thinking about them in more this generality, you will discover new interesting things. That's basically what
that's what mathematicians do all the time.
Yeah.
And this is like what algebraists do on steroids, right? In some sense.
Yep.
Okay, so let's see. So I feel like we've skirted around it, and it's now time to at least try to define what synthetic mathematics is in this sense. You want to give it a shot?
Sure. Okay. So first of all, I don't think this is a precise notion, like a mathematical precise notion, but it's a phenomenon that has now happened so many times that it deserves a name. And the idea is as follows. You have some mathematical topic or a branch of mathematics that you're interested in, say computability theory or algebraic geometry or topology or differential geometry. Think of something like that, like a fairly wide branch of mathematics. And then you say, okay, so the way that this branch proceeds normally is that it builds up some machinery that it needs in order to actually start functioning. So if this is computability theory, you start by explaining what a Turing machine is and what a tape is, and then you prove a bunch of things about machines, and there's a universal machine, and there's the SMN theorem, blah, 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 blah. And you have to prepare a foundation, right? You're building up a base of knowledge, and the actual sophisticated computability theory that you're really interested in comes on top of that. And it's going to be the same with, say, let's take differential geometry, right? So differential geometry, what's that about? Well, that's about tangent spaces and these differential forms and things like that. But how do you get there? Well, very carefully. Natural numbers, then you build integers, then you build rational numbers, then you have to teach somebody reals, then they have to do several years of real analysis to learn what continuous means and what the definition of the derivative is, and then you do then you do smooth functions in R to the n, then you define what a manifold is. There is a lot of knowledge, and so then
basically the
you don't
first
need-
line we assume X of every paper. Like that's this huge.
Right. So somebody who wants to read the text in sort of core differential geometry will be familiar with all these things. However, at the same time, the ideas that differential geometry studies are very intuitive and quite old, right? The idea of a derivative did not arise by Newton first defining Dedekind cuts and defining, like, he just went straight for these naive, nowadays we call it naive idea of what an infinitesimal is and how that gives you notions of differential, what we would now call maybe differential geometry, right?
Sure.
So one wonders, what did go, why did people do this? Well, people did all of this because there were problems with what Newton and Leibniz were doing, and people were doing weird stuff with infinitesimals that didn't make any sense. So they wanted to secure a better foundation, so they built this whole edifice. Okay, that's the story. But is this really the necessary way to go? Why? We can take a second look at how differential geometry works and say, hey, why wouldn't we just literally axiomatize that there is a ring of reals, okay, that's easy, and that it's got some infinitesimals in there, right? And algebraists will tell you, yeah, sure, you can do that, right? They will say, yeah, of course. You just say like R, take the polynomial ring R of X modulo X squared, kill X squared, right? And you're going to get something that looks like infinitesimals. But the next move I'm going to make will stun the algebraists. The next move I will say, and every function is smooth. That's now a little harder to swallow. They'll say, well, you don't mean every function, right? You mean certain functions are smooth. And then I will say, no, all functions need to be smooth, right? And then I'll say, well, but you can't have that because I'm just going to define a function that is not smooth, right? So we're now getting to the crux of the matter. I will say, okay, how did you define it? And however they defined it, I know in advance that they used excluded middle. So I will take that away from them, and suddenly they're not able to define a non-smooth function. Well, actually, they still will be able to define something like the absolute value, but it won't be defined everywhere on my R. So they will not be able, once you take the excluded middle away, you cannot exhibit that things will go wrong. In fact, there will be models where things go right. And so what happened here is we sidestepped this entire business of building this, starting from classical set theory, building something on top of which is the thing we really want. And we say, can we go directly for the thing we really want?
Okay, so let me try to paraphrase what you're saying, and you can tell me whether that was your intent or even if what I'm saying makes sense. So you say, take a mathematician, take a field of mathematics, take the bread and butter of the structures that they care about. They've built an elaborate machinery to be able to define these structures and talk about, the objects involved or the morphisms involved, or, the higher. That machinery is complex in some sense, perhaps because there might be a simple set of axioms to talk about these objects, but these simple set of axioms to assume that they're true everywhere is not false, and to build an object where they are true everywhere in classical mathematics is subtle. So now you go back, you figure out which axiom you use to build counterexamples to those, you remove them, and then you say, hey, let's look at the mathematics without these axioms that I used to build all my funky counterexamples. And then maybe your naive axiomatization can be sort of generally true. Your counterexamples basically just don't even exist. And that, you can work in that world of slightly weakened world of like axiomatic set theory or foundations. and kind of be happy because you know that all the things you prove will hold in the realm that you're interested in. Is that kind of a
Yeah, I think that's a very good description of it. You are trading a little bit of logic for
a lot of
for an ideal, what you consider to be the ideal situation, which the logic is telling you is impossible, right? So classical set theory is going to say, no, excuse me, but you cannot have all functions on reals are smooth. You cannot have that. Right. And then you say, okay, why can I not have that? And you see that this thing that you really, really want, namely that you can just freely take derivatives of functions on the reals, is in opposition with one of the laws of logic. Why wouldn't you throw away the law of logic? Well, right? Well, you wouldn't take it away. You will want to keep it if your math becomes unworkable without it. So does math become unworkable without excluded middle? Bauer and Hilbert both thought yes, but the answer is no. It is still quite workable, right?
Sorry, you said Bauer and Hilbert? I expected Hilbert, but now Bauer is surprising me a little bit.
So this is a remark that Michael Beeson makes in his book, which I like very much. Both Bauer and Hilbert expected that large swaths of mathematics will disappear once you remove excluded middle. And it was really Bishop in 1967 with his book that just showed that this is simply not true.
Fantastic. I was going to talk about Bauer and Hilbert and Bishop, but thankfully you did it for me.
So yes, so and this is, I think, is a general situation. It's just that you need to get, as a mathematician, you must stop thinking about logic being special. It's not a holy cow. If you are able to mold your definition of space or whatever you study, if you're able to mold it to your desires, you should be able and brave enough to do the same thing with logic. This is not that different.
That's a very good slogan. And this is why I wanted to have you on the show, is your ability to sloganize these somewhat non-trivial ideas.